a recap of the electron configuration worksheet. The number of sublevels is equal to the energy level. So for instance, when n equals 3, we have 3 sublevels because it goes from n minus 1 down to 0. If at n equals 3, we can have 2, 1, and 0, which represent S, P, and D. And specifically, we'd be talking about the 3S, the 3P, and the 3D. So the sublevels go alphabetical after F. So the S, P, D, and F actually stand for, it just doesn't matter, but they stand for spin, principal, diffuse, and fundamental. And they have to do with the spectral lines that were used to recognize those sublevels. Like for the D orbitals, the spectral lines are very blurry. But at any rate, so whatever reason they chose S, P, D, and F, after F it goes alphabetical, G, H, I, J. So this is for values of L, right? When L equals 0, S, and so on. Okay. The number of orbitals in a sublevel, or which is related to different orientations the orbitals can have, is related to this M sub L number. And the M sub L quantum number goes from positive L to 0 to negative L in integer form. So the idea is when when L equals 0, like an S, then there's only one orientation. There's only one orbital in that sublevel. When we have a P, which has an L of 1, there's 1, 0, minus 1. We get 3 sublevels, right? And we would expect D to have 5 and F to have 7, and so on. The number of electrons in those sublevels is 2 times the number of orbitals. So if I have 1 orbital, I can have 2 electrons. If I have 3 orbitals, I can have 6. If I have 5 orbitals, I can have 10. So the number of electrons is 2 times the number of orbitals. All right, let's continue. The number of orbitals in an energy level. So we're not talking about the order of filling, but just how many electrons are in the 3rd energy level? How many electrons are in orbitals that have a 3? Or how many orbitals are in an energy level where it has a 4? And so the rule, the number of orbitals is equal to n squared. So for instance, when n equals 1, 1 squared is 1. There's only one S orbital, and that's it, right? When n equals 2, 2 squared is 4. There's an S, and then there's 3p for a total of 4 orbitals. When n equals 3, then we would expect, and 3 squared would be 9, which stands for an S and 3 P's and 5 D's, right? 1 plus 3 plus 5 equals 9. The number of electrons in an energy level is equal to 2n squared. So because I can have 2 electrons per orbital. So if there's only 1 orbital, then I have the first energy level can only have 2 electrons. That's why in the first period, there's only hydrogen and helium, right? In the second energy level, where I have 4 orbitals, I can have 8 electrons. And so that's why the second period is 8 atoms across, ending with neon, starting with lithium, right? And so on. Okay. Reminding ourselves of the filling pattern on the periodic table, that for S and P, the energy level is equal to the period. So just looking at the periodic table, if I'm in the second period, beryllium would be 2s2, right? Or if I was looking at phosphorus, it comes from the 3rd period, that would be 3p123, or actually 3s2, 3p3, right? So for the S and P, the energy level is equal to the period. For the D, the energy level is equal to the period minus 1. So for the D, so in the 4th period, this is the 3D, right? We go 4s1, 4s2, 3d1, 2, 3, 4, 3d10 at zinc. If we went down to the 6th period, this would be the 5D, right? So platinum would be expected to be 5d8, mercury would be 5d10, and so on. When we go to the F, The energy level is equal to the period minus 2. So when down here, this F block here, which starts with lanthanum, also called the lanthanide series, comes from the 6th period. So we go 6s1, 6s2, 5d1. We put 1 electron in the 5d, and then we go down 4f1, 2, 3, 4 to luteum, which would be 4f14, and then we go back up 5d2, 5d3, right? So the F is actually came from the 6th period, so this is the 4f. This F came from the 7th period, so this would be the 5f, right? We'd go 7s1, 7s2, 6d1, 5f, 1 through 14 to Lawrencium, and then back up to 62, 63, so on. Okay, so that's that. The periodic table is really your best friend for doing the electron configurations, using this and following Hund's rule. Okay. So we saw noble gas configuration is the configuration of a noble gas, which generally, noble gas configuration means having an S2P6 for whatever energy level. The condensed electron configuration was you remove all of the electrons from the previous noble gas and you put the symbol of the noble gas in brackets, and then you show the other electrons normally. So if this is the full electron configuration of sodium, sodium element 11 has the most previous noble gas of neon, which is element 10. Neon, of course, let's put neon on the side. Neon equal to 1s2, 2s2, 2p6. So again, that following this, the noble gases with the exception of helium are always s2p6. And then, so we put neon in brackets, so meaning sodium has the electron configuration of neon plus 3s1, right? And so that's doing the condensed electron configuration. We saw that there were some exceptions. There's actually more exceptions than these, but these are actually the first exceptions we see on the periodic table. We're going to ignore exceptions in the F block. There's tons of exceptions in the F block, actually. But these ones we can actually explain pretty easily from a quantum mechanical perspective. Chromium and copper and the elements directly below them in their period, or in their group, I should say. So they take 1 electron from the higher S and give it to the D. The D becomes lower in energy. So so elements that are starting to fill the D block, filling the 3D, have a full shell up to argon. So the expected for chromium was argon 4s2 3d4. But the actual, when they do the actual quantum mechanical calculations, what's actually lower in energy is argon 4s1 3d5. So that perhaps was unexpected, but when we look at it and say, okay, it steals an electron, maybe I should show that in red or something, pink. How about pink? Okay, I'm gonna use pink. It steals an electron from the S and gives it to the D. When it does that, it gets a half-filled D block, and it lowers the energy of the D block, making it lower than the 4s. So that's the explanation. So copper has a similar motif. This is the expected electron configuration of copper, 4s2 3d9. Actual, again, steals 1 from the S, gives it to the D, and you get a full D block. The full D block is lower in energy than the 4s. Also note that elements below them in the same group do the same thing. So molybdenum, tungsten, we would expect to be D5. Silver and gold we expect to be D10 exceptions, right? So for answering some more orbital filling patterns, we remind ourselves that main group elements are the groups 1A to 8A, the tall columns. They can also be called representative elements. It's just an older name for them. Okay. And so there's some filling patterns. So usually, well, before I do paramagnetic and diamagnetic, representative elements are usually filling the S and P blocks. The transition metals are filling the D, and the inner transition, the actinide and lanthanide, are filling the F, right? And you have to be specific when you answer those questions. Paramagnetic and diamagnetic. Paramagnetic is an atom or ion that has one or more unpaired electrons, and these types of atoms will interact with the magnetic field. You can be paramagnetic, other atoms, not just odd numbers, but you can have some even numbered atoms that follow Hund's rule that can have unpaired electrons, such as carbon, which is, I have an even number of electrons, 1s2, 2s2, 2p6, but because of Hund's rule, filling the p block singly, I have unpaired electrons. So a single atom of carbon would interact with a magnetic field. Diamagnetic, an atom or ion that has all electrons, I should say paired. Okay. And these kinds of elements avoid magnetic fields. And just having an even number does not mean you're diamagnetic. Actually, diamagnetic is very restricted, at least for atoms. For things that are bonded, there are other things that can bond to get diamagnetic. But any atom that ends with S2 or ends with D10, not an exception, or ends with P6 or ends with F14. So it's a very, very small group compared to the overall periodic table.